2, 1. Here we go. All right, so we are on example 6. We got example 6, example 7, example 8, and example 9. So we can get those done. All right, example 6, an application. Find the coordinates of any points where x, e to the x has a horizontal tangent line. So again, coordinates usually implies x comma y. If we can find the x values, finding the y values is not a big deal. We can just plug them each in, or however many there are, into f of x. So that's kind of the main task there. But you do want to answer the question. So find the points on this graph where we have horizontal tangents. So what's our plan? What do we do? What's the slope of a horizontal line? When the numerator equals 0, or when the whole what equals 0? Derivative. Yeah, it's when the derivative equals 0. So like when you're evaluating limits, right, and you don't know what to do, DNE is a good answer. If you're doing differential calculus and you don't know what to do, taking the derivative and setting it equal to 0 is a pretty good thing to do. So let's do that. So I'm going to put parentheses around here. I have 2 variable factors, right? So this is the product rule. 2 factors means 2 terms. So f prime of x is, the derivative of x is 1. E to the x goes along for the ride. Plus x goes along for the ride times the derivative of e to the x is e to the x, right? Now, someone who doesn't know about the derivative of e to the x, but they know about the product rule, they might think that we didn't even take the derivative right there on the highlighted part. But we did, didn't we? It's the same. And we sing the grandpa song to him, right? Now we set it equal to 0. Set it equal to 0. And of course, once you have multiple terms and it's equal to 0, your job is to solve it by probably doing what? F'ing it, F'ing it, F it, right? And the F word in here is, of course, what? Fun. I know it's fun. Factor. Yeah, factor it. When it's equal to 0, we try to factor it. Hey, we happen to have a common factor. His name is e to the x, and that leaves us 1 plus x. Oops, I put it equal to e, not 0. And now the 0 product property says that either e to the x equals 0 or 1 plus x equals 0. Let's do the linear one first. 1 plus x equals 0 when x equals -1. Is e to the x ever 0? No. No, you're not going to take a numeric base and raise it to any power and make it 0. It can approach 0. There's a horizontal asymptote there, but it's never 0. So this piece has no solution. But we do have 1 x value. And now if we want the coordinate, we could say, so f has a horizontal tangent line at the coordinate -1, and then all we got to do is plug it back in up here. F of -1 is -1 times e to the -1st, which is negative e to the -1st, right? You just plug it into the original function. Or if you want to rewrite that, it could be -1 over e. That's the same thing, right? E to the -1st is 1 over e. So that would be the coordinate. And that one was not difficult to find. So that might be an actual question where you have to find the x and the y coordinate. Okay, cool. Do we know what the equation of the horizontal tangent line is? We can use Taylor form, but that would be kind of like driving in a brad nail with the sledgehammer, because remember, a horizontal line is of the form y equals a number, yes? And if it's going to be a horizontal tangent line and it's going to glance off of this point, it'll share the same y value as the y value it's tangent with, yes? It has to be, right? If this is the point right here and there's a horizontal tangent line, the point and the line have the same y value. So the equation of the tangent line, in this case, is y equals -1 over e. You might be asked for the equation of the tangent line. And if you know it's horizontal, you don't need to use Taylor form. Taylor form would still work, wouldn't it? Remember, Taylor form would be the y value, which is -1 over e, plus the slope of that line times x minus the x value. But 0 times anything is 0, so you don't really need that. Okay, cool, nifty, a little application of e to the x. And truth be told, you see e to the x probably 99% of the time on the AP exam, but every once in a while they'll throw like a 2 to the x at you just to make sure You remember to multiply by the natural log of 2 or something. Okay. All right. Letter 7. Ooh, look at this one. Find the equation of the tangent line to y equals that at the point 1 comma e. 1 comma e. So they're giving you the ordered pair. So we already have the x and y value. So we're 2/3 of the way there. All we need for the equation of a line is a point and a slope, an x coordinate, a y coordinate, and a slope. We have 2 of those. So we just need y prime of 1. That's all we need. We need the slope of that line or that graph. Wow, look at how many terms, 3 terms. And then the first term has 2 factors that are variables. The second term has 2 factors that are variables. And the last term is just 2e to the x. So we could jump in and start doing double product rule. But is there anything we could do in the beginning that might make it a little bit easier? We can factor out e to the x before we start. Simplify early and often. Size up the problem. E to the x, when we factor it out, gives us x squared minus 2x plus 2. Now, if we take the derivative, it's just a single product rule. 1 is fewer than 2. I like that. So on the left side, we'll put y prime or dy dx. It's explicitly solved, so we don't need d dx. And you can put e to the x in its own parentheses if you want. So here we go. The derivative of e to the x is e to the x times the second one goes along for the ride. And it just seems like we're rewriting that, huh? Yeah, we did. Plus, now e to the x goes along for the ride times the derivative of the second factor, which is 2x minus 2. All right. We don't want to set this equal to 0. We want to evaluate it at the point 1 comma e. So notice we really only need the input value. So would you plug in and then simplify, or would you simplify and then plug in here? I would probably simplify and then plug in. I would probably do the other, but okay. Because we're only after the numeric slope, right? This will simplify nicely though. Let's go ahead and do it since that's what y'all said. We have 2 factors and there's a common factor of e to the x. You're going to see this type of problem manifest quite a bit when you have exponentials, because by nature, they're going to generate themselves in each term. So you're going to be factoring it out a lot. So we're left with x squared minus 2x plus 2. And we factor it out of the second, we're left with plus 2x minus 2. Now notice I don't need parentheses around the 2x minus 2 because the only thing that is in front of it when I pull the e to the x out is a what? A plus 1, right? Had that been like a minus e, then I would need to distribute the negative. So little things like that, algebraically, you want to be diligent about. And then simplifying by combining like terms, let's see, I get x squared. The minus 2x is cancel and the 2's cancel. So this does kind of simplify nicely into x squared e to the x. It's pretty handsome, right? Cleans up nicely. Spiffy little dude. Well, we could have plugged in the number first and then simplified just as easily, but now we can plug in. So we'll say y prime of 1. That's the x value up there. We get 1 squared, which is 1, times e to the first, which is e. The slope is e, 2.718. Nice. And now we can answer the question, right? I'll do it over here. So the equation is in Taylor form. Let me get my ingredients right in front of me here. The point is 1 comma e, and the slope is e. Look at that, m is e. Okay, so the equation is y equals the y value of e plus the slope e times x minus the x value of 1. So there it is. Bless you. That almost looks like Kanye West's new name, doesn't it? Yeah, Yexel. I don't know. Now, if this were a free response, we could be done. But what if this were a multiple choice question? That's not going to be an answer choice. So let's go ahead and distribute. Y equals e plus e times x minus e. And what happens with the e's? They cancel, and we're left with y equals e times x. And is that correct? Yes. Yes, that's correct. It seems like a word, like it should be a word, right? Yes, yes, no, no's, yes or no. How them blues and berries?
Good.
Good, 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 good. Yes, Brody. The derivative of the original function.
The derivative, when we simplified it all the way down, it was x squared times e to the x.
Yeah.
And then the original function, the first term is
Oh, x is x squared e to the x. Yeah, yeah. That's what do you call that? Inception calculus. Yeah. Yeah. I mean, and a lot of it is because e to the x is inception, right? It's his own grandpa. Maybe instead of playing that song before e to the x, we should just watch the whole movie Inception first. Yeah, it is good. Yeah, that's a keen eye, Brody. I didn't notice that. All right, so you ready for another? I am. Oof. Number 8, find dy dx for e to the xy plus x squared minus y squared equals 10. I think you were the one to ask, Ella. Are we going to be doing all this stuff implicitly ever again? Are we ever going to see implicit ever again? And the answer was yes, right? Here we have an implicit one, right? Because is it solved for y? No. Do you want to try and solve it for y? I don't. Because I have a y trapped in an exponent on the e, and then I have one on the ground floor. And freeing one enslaves the other, and that's not fair. So let's just jump in and take the derivative. Now, this is where we have to show d dx colon. We have to indicate our method. That means, hey, what follows the colon is the derivative, okay? How many y's do we have in our equation? 2, one here and one here. How many dy dx's should we walk away with? 2. Okay, good. So the first term is e to the blob, right? E to the blob. What's the derivative of e to the blob? E to the blob, e to the blob, right? And now you go up there and you take a look at the blob and you're like, what's up, blob? The blob is x times y. How are we going to differentiate that? It's the product rule. Yeah. The derivative of x times y is the product rule. We better have parentheses there, yes? Because we're fixing to generate 2 terms. All right, so I'll use a different flavor here, orange. The derivative of x with respect to x is 1 times y goes along for the ride, plus x goes along for the ride times the derivative of y with respect to x, which is 1, or just dy dx. See those extra sets of parentheses, the purple nurple ones? Yeah. It would be so unfortunate to know what you're doing, but like not have those purple parentheses there. And then that second orange term is not even involved with, e to the xy anymore. So there you go. So that just takes care of that. That was cool. And now we move on to the next term, which is plus x squared. So that's plus 2x dx, which we don't need, minus the derivative of y squared, which is 2y dy dx, which we do need. And then the derivative of 10 with respect to x is 0. And do we have 2 dy dx's? Indeed, we do. All right, now we have to solve for dy dx. The dy dx on the right-hand side, close to the equal sign, he's ready to play, isn't he? He's ready to play. But as we saw earlier, this dy dx, he's trapped inside the purple house. And he can't come outside to play until he does his chores, right? We can only collect like terms, and he's trapped inside right now with this factor holding him hostage, if you will. Mom, right? Do your chores. So how do we liberate this term with the dy dx? We simply distribute. Yeah. You might at some point think that dividing by e to the xy would also work, right? Which in truth, it would get rid of it from here. But then when you divide every term by e to the xy, it frees this one up. But now you're going to have this third term all over e to the xy. And again, that would lock him up. So distributing, when in doubt, just distribute it all out, right? And then collect like terms. So distributing that, we get y e to the xy. That's a good way to write that. Plus distributing there, you get x dy dx e to the xy. It's customary to write the e at the back end because otherwise, you know, everything's butted up against the elevated exponent and just stylistically it looks bad. And then plus 2x minus 2y dy dx equals 0. So that wasn't too bad. Now here's one term. There's the other term with the dy dx. We're ready, since they're already on the same side, we're ready to factor that out, aren't we? So let's do that. We get dy dx times, and in that first underlined term, we're going to be left with x times e to the xy. And in the second term, we're left with minus 2y equals. Now, everything that I did not underline is going to go to the other side, and the sign of the terms changes. So they're both positive, so now they become both negative. Minus y e to the xy minus 2x. All right, and now all we do is divide both sides, and it divides out on the left, and we're left with negative y e to the xy minus 2x all over x e to the xy minus 2y. This would be a good free response question where they would say, show that dy dx equals something, or a multiple choice question. In either case, this would not be the one that they would have you show or get to the final stage at, because notice we have 4 terms and 3 of the 4 terms are negative and only one of them is positive. So I like College Board in this respect. They like to, you know, suppress the negative and highlight the positive. So what can we do to make it equivalent, but, you know, give it a complete makeover optimistically? Remember what we did? Multiply by -1 over -1, right? What happens if you multiply by -1 over -1? It doesn't change the value, does it? All it does is it changes the signs of everything. If you distribute that -1 all the way through, it's going to be positive 2x and now positive y e to the xy. Why did I commute those terms in the numerator? Well, I'll show you. When you distribute the negative in the bottom, you're going to end up with a positive 2y and now a negative x e to the xy. And we typically like, if there's a positive term and a negative term, we don't like to lead with the negative, just because it's bad, right? When I walk up to you and say something negative first, and then, oh, by the way, I didn't mean that, you know, you get to know the person first, and then you say something bad about them, right? That's better. No, when you have a negative floating around out front, it can get lost, right? It can get damaged, it can get overlooked. But when you have a subtraction, you know, it's a little bit easier to see. All right, so just keep that in mind. If you would have selected or collected your dy dx's on the other side of the equation, you would have come up with that answer. So typically we commute the terms. So this would be the preferred answer right here. All right, fun, right? Implicit differentiation. Lots of fun. E to the x, though, easy, right? E for easy. Last one. Find, I forgot what this meant. What does this mean? Second derivative, right? If y is equal to that. Okay, crap. What's the formula for the second derivative? Right? There you go. Right. If someone asks you that, you're like, dude, do you even know what calculus is? You're like, not really. But I'm sure there's a formula for it, right? If not, why have you not invented one? We got to do it recursively. We got to go through the first derivative. So is this one explicitly solved for y? Yeah, it's y equals and then no y. So that's good. Anything needs to be rewritten? Nah, I don't think so. It looks pretty good. The only thing I might do is kind of put parentheses around the -3x because it's 5 to the blob. It is exponential, right? Numeric base, variable exponent. All right. Oh, Hank. Yeah. All right. No more third party for Hank. All right. You're going to bed after party number 2. All right. So let's go ahead and take the first derivative here. Because it's explicitly solved for y, we just go straight to dy dx. And now it is a product rule, right? So if you want to put extra parentheses, you can. That was not nice, Hank. You can get him back when y'all are in uniform. I don't either. The back of your head looks the same to me, whether your eyes are open or closed. Okay. So here we go. The derivative of the first factor is 0 plus 2, or just 2, times the second factor goes along for the ride. Plus the second term is going along for the ride times, and now we have the exponential piece, right? The derivative of 5 to the blob is 5 to the blob. There you go, Mason. Shh. Eugene, Eunice, go to your own rooms. Natural log of 5. Don't forget the natural log of 5. And then times the chain rule, the derivative of negative 3x, which is negative 3. I put parentheses there. I'm thinking maybe I don't need them, right? If I just put dot negative. Grrr, grrr. Okay, there's the derivative. So I can go straight to the second derivative. I really can, but it might pay dividends to tidy up a little bit, right? Okay, so yeah, for sure it will actually. Notice that there is, again, a common factor of the exponential piece. It's not e anymore, but it's still exponential. It generates itself in part, you know. So let's go ahead and do a couple of things. We'll factor out the 5 to the negative 3x, and then we'll clean up each term with what's left. In the first term, there's really only a 2 that's left. And in the second term, we get a minus 3 natural log of 5 times the quantity 3 plus 2x, close, close. And I'll bring dy dx down again. All right, now it's up to you whether you want to take this and distribute it. What do you think? Would you be okay taking the derivative like that, or would you be more comfortable distributing it? You don't have to respond to my question or the board, either one.
Respond to both.
Yeah, what would you distribute the minus 3 ln of 5? Early and often? Yeah, I would think maybe it would prevent you from making careless mistakes, you know. You could do it with it sitting intact, but you know, getting rid of parentheses might make it easier. So we'll distribute it. 3 times negative 3 natural log of 5, I can multiply the 3 together and get minus 9 natural log of 5. And then the next one would be minus 3 times 2x. That's minus 3 times 2 is 6 natural log of 5. And here's where you got to be careful. Times x, right? Or put x in parentheses or put a dot there, because this is the coefficient of x, like the e cubed x that we saw earlier. That's a linear term. It just has a wacky coefficient, right? And if you didn't put a dot there or parentheses, it might look like 6 times the natural log of 5x, right? And x is not in the argument. It's, there you go. All right, now let's take the derivative one more time. So the derivative of the derivative on the left is the second derivative. And now, oh, look at this. We got a product rule again. The derivative of the first is itself times the natural log of 5 times negative 3, the chain rule. And then the second goes along for the ride. I'm just going to copy that because we have notability. Boom. Okay. So we took the derivative of this, and that goes along for the ride, plus the 5 to the negative 3x goes along to the ride. And now we're going to take the derivative of the second piece. And this is why we expanded it. 2 is a number, minus 9 natural log of 5 is a number, right? There's no variable in it. What's the derivative of a constant? 0. So those two highlighted terms go away to 0. And then as we saw earlier, what's the derivative of a linear term? If it were 5x, it'd be 5. If it were 10x, it'd be 10. So it's just the coefficient, right? So it's just going to be minus 6 natural log of 5. And then I close. Yeah, no, that's it. That's it. So All that would be left to do is maybe factor out another 5 to the negative 3x, and then do some other razzle dazzle. But right there, we're done essentially. Okay. So if you can follow along with that, we have wacky coefficients, natural logs and e's, all part of the rest of the year now. So we're going to skip example 10. I'm not really a big fan of it. If you want to graffiti this guy, he's kind of inviting you to graffiti him, really. Yeah. But at this point, if you want to submit your notes or wait to submit them later, on Monday and Tuesday of next week, we'll do the last section in chapter 2. We'll learn all about logs. We'll review the properties of logs, the rules of logs. We'll learn how to take the derivative of something that has logs in it. We'll modify our mantra of simplify early and often. We'll add an addendum to it. And then I'll teach you something that's not on the AP exam called logarithmic differentiation. So anyway, y'all have a great, fantastic weekend. We'll see y'all, some of y'all at the game. Unless you see me first, right? I guess.